All right, so we're doing lesson 3.7, transformations of graphs of linear functions. Okay, so some of y'all are asking about why are we doing chapter 3 now? Today is kind of air quotes a new lesson, but not really, because what we're doing is we're bringing together the transformations that you've already been seeing on those quadratic parabolas, the transformations we've been discussing like horizontal and vertical stretches and compressions, reflecting across the x-axis, translations, and we are putting that together with linear functions. We spent a lot of time in the fall working on. Okay, so we're taking two familiar things and then just looking at them together. So the same transformations that we've been doing on the parabolas, we're now going to do them with lines, linear equations. Okay, and you're right, this is chapter 3. So if you're wondering why we didn't do this back in September or October when we were right in the mix of linear equations, the reason is because I at least personally feel like a lot of these transformations are very hard to see with a line. Okay, so a vertical stretch is a lot easier to see on a parabola than it is on a straight line. Even translations themselves are very hard to see on a straight line versus on a parabola. It's really obvious when that curve moves to the side or up or down. It's not very obvious with a straight line, okay, just because of the nature of the graph itself. So I've always felt like it's easier to introduce those transformations with the parabolic curves because visually we really can see it in action better. And then once we have a good idea of what those transformations are, then we go back and say, hey, you can do this with lines as well. And really, hopefully, when you walk out of here today, you'll feel like, actually, I can do this with any graph. And that's the huge thing I need you to walk away with. We're going to practice it with linears now because we didn't do it in the fall. But the bigger idea that I hope you leave here is that a +5 on the outside of the function is going to translate that function 5 units up no matter what the function is. It doesn't matter if that function is an exponential curve, a linear curve, a quadratic curve, a cubic, a square root function. Whatever it is, that +5 just moves it up 5 units. It could be a circle. It could be a car. I don't care what it is. If it says +5 on the outside, it's shifting it up 5 units. Okay? So this whole lesson is to just make these transformations more universal, and hopefully you'll understand that they're not specific to a parabola or even to a line, that these transformations will happen the way that we describe and we talk about no matter what your original curve shape was. Does that make sense? Okay, and that's why on the little half sheet that you picked up on the way in, which I think will be very handy as you get studying, study this and get comfortable with it. If you look at that half sheet, it gives you the description for each of those changes, and it says nothing about whether f of x is linear or quadratic or exponential, because that's the point. It doesn't matter. It doesn't matter what f of x was. If I multiply it by 2 on the outside, it's going to be a vertical stretch by a factor of 2, regardless of what it was originally. You see, that part is pretty much irrelevant. Okay? So this is what the transformations do, regardless of what the function is. That's kind of the big idea. And by the way, one last thing, easily 60 to 75% of Algebra 2 is on that half sheet that is in front of you. Okay, over half of the year that you spend in Algebra 2 in a year and a half from now is spent just studying and watching these transformations happen with different families. Like we do it in linears and quadratics in Algebra 1. They do it with absolute value functions, exponential functions. They do it with square root functions, cubic functions. They just basically, they introduce you to more families, but then it's really just all about those transformations on that half sheet. That's over half the year in Algebra 2. So I've never said this before, and I'll probably never say it again, but if you nail this lesson today, you pretty much can check off that you've got half of the year of Algebra 2 next year, honestly. This is like at the core of over half of their curriculum. Okay? Yes? That's very interesting that you bring that up. We are literally in the middle of that conversation right now, and that's going to depend on, so here's the deal. The test is on Monday, and it's really close to the end of the quarter. So what is most likely going to happen, but we're going to seal it in stone, so don't record me while I say it. Just kidding. Is we are looking at not offering a retest on Chapter 8 because it's so close to the end of the quarter, it would be almost impossible for us to get those grades back from the retest, but letting you use the half sheets instead. But that really means y'all have to prepare and be ready to do well the first time because there's probably not going to be a retest next week for Chapter 8, okay? But don't quote me on that. I will have a solid answer for y'all probably by tomorrow, okay? All right, are y'all ready to start looking at these? Okay, so again, you've seen this before, and you've seen it with parabolas. We're just going to see it with lines. And again, hopefully you'll just see that it's really the same for no matter what graph it is, okay? So first of all, let's talk about translations. So we know that translations are simply a transformation that shifts or slides our parabola either horizontally or vertically, okay? That's going to happen anytime you add or subtract a number to your function, okay? So the translations happen when we add or subtract a number. Okay? Now, we've said this a little bit before, but if the change is happening inside the parentheses of f of x, remember, f of x, that function notation, is designed so that whatever's in the parentheses is your input. Do you remember that, right? When I say f of x, or f of t, or f of r, whatever's inside that parentheses, that is our input. So every time we see any change happen inside that parentheses, it is happening to our x coordinates horizontally on that x-axis. Okay? So if you see it happening inside of the function notation parentheses, you know that it's affecting your x input, your domain. And that's the x-axis. And the x-axis is horizontal. So you can expect to see horizontal changes every time the change is happening inside the grouping, that parentheses, okay? So inside the parentheses, it is horizontal. So when we add or subtract inside of that, we're looking at a horizontal translation either to the right or to the left. Because when we are, adding or subtracting that age, that is affecting the input before we evaluate the function, right? We're changing the x input before the function is applied. Okay? If it happens after, outside of the f of x, the addition or subtraction, then we're adding or subtracting to the output of f of x. We're basically evaluating f of x first. We are figuring out what that output was. And then after the fact, that output is being added or subtracted with k. So that's happening to our output, which is which axis? The y-axis is our outputs, right? Our answers, yeah? So that's vertical, right? So anytime it happens outside of the f of x, we're looking at a vertical transformation. And since this is addition subtraction, it's a vertical translation. So adding or subtracting a k to the output on the outside shifts things or translates them up or down, depending if it's addition or subtraction. Okay? But this is a good picture for me to kind of drive home the reason why I did not do this in the fall. You can see right away that if we didn't have these arrows, if you just imagine those arrows not being there, really this graph looks identical to that graph. Even though one was moved side to side, the other one was moved up and down. You see how the lines really look the same. This is very challenging to really get the concept of that when the line looks still exactly the same one way and the other. That's where it's a little easier to see on a parabola and get the idea first, and then go back and say, okay, I understand what's going on with those lines, even if we can't really see it. Okay? So that's why we waited until now. Okay? All right. So last couple of things. Remember, if it's on the inside, it's horizontal. If it's on the outside, it's vertical. Last thing, remember the horizontals, they tend to kind of work a little bit in reverse or backwards a little bit. So when we see minus h, we're actually moving to the right. If we see something like x plus h or x plus 7, we're actually moving to the left, right? So things tend to kind of work in reverse in the parentheses, right? And we'll see another example of that with the horizontal stretches and compressions. All right, so adding and subtracting translates. Signs, just positive and negative, reflect, okay? So a reflection is a transformation that flips the graph over a line of reflection. Okay? And the only thing that will ever cause that reflection is just a sign change, either outside or inside of that function notation. Okay? So just like what we discussed, if that sign change happens outside of f of x, then we're looking at the output's changing sign. Does that make sense? The output is changing signs. So let's say, for example, at this point right here, my output was 5, and then I reflect that output, it would be down at -5, right? So we're looking at a reflection that reflects vertically up and down, but my line of reflection is the x-axis, right? So I'm reflecting my points up and down, right? Because my y-coordinate, my output is changing. But the line of reflection is the x-axis. That's what I'm rotating around. Does that make sense? Okay. If the sign changes on the inside, then that's happening to my input. And my x input is changing sign before the function is applied. So that means my x coordinates are the ones that are being changed. Perhaps my x-coordinate here was a -2, and maybe that moves to a +2, but it's my change is happening side to side along the x-axis. It's my x-coordinates that are swapping signs, but that means that my line of reflection is which axis? The y-axis, right? So if I'm rotating side to side, right, my y-axis is the line of reflection for that. Okay, but what's changing signs are my x-coordinates. If my x-coordinate was a -10, it becomes a +10. If it was a +10, it became a -10. So that's the way that it's reflecting side to side. Okay, and that's all that positive and negatives do. They just reflect. Okay, if we are multiplying by something other than 1, right, and we have an a value, this is where the stretches and compressions happen, or the stretches and the shrinks, when we multiply by that scale factor, right? And we talk about, oh, it's a vertical stretch by a factor of 3, or it's a vertical compression by 1/2. So that's when we actually are multiplying by a number, okay? So when we are multiplying by a, that causes stretches or compressions. Again, if it's on the inside, then we can expect it to be a horizontal stretch or compression. And remember, for those, our scale factor is the reciprocal. So that's a little similar to the whole minus and plus going right and left, you know, being a little bit in reverse. Same thing here, right? So if our a value is 2, for example, then that's actually a horizontal compression by 1/2. Okay, so it's the reciprocal. Your scale factor is the reciprocal of whatever your a multiplier is. Okay, and we're looking at that from a horizontal point of view. Okay, and if our multiplier is on the outside, then we're looking at it from a vertical point of view, and it's a vertical stretch or shrink. Vertical ones are always a little simpler. What you see is what you get, right? If it's multiplying by 3, vertical stretch by 3. If it's multiplying by 1/3, vertical compression by 1/3. So it's a very direct. Just like with these guys. Oops, sorry. Right? This was very much what you see is what you get. If it's +7, you went up 7. If it's -4, you went down 4. Where here, it's kind of the reverse, right? If it says +5, I'm actually going to the left 5. You know, if it's x minus 3, I'm actually going to the right 3. So that's where the horizontals tend to kind of be the reverse of what you see in the equation a little bit. Okay, so when we're multiplying, that's what causes the stretches and shrinks. And we've dealt with these guys before. We did spend some more time on this on the parabolas. We're just going to see it with lines. Okay, so as we practice these, this is just a nice little step-by-step if you need that. As we practice this, here's at the heart of it, guys. Especially the first 3 examples, they have graphs, and they tell us what f of x is. But if I'm going to be bluntly honest with you, the graph doesn't really matter. And the actual f of x function doesn't really matter, because in this particular unit, all they're asking us is what transformation occurred to get us from the f function to the g function. And if I understand what that does, I can describe that even if I didn't have the graph in front of me. Okay, so sure, I have a graph of f of x and it's 1/2 x, but that actually doesn't really matter, because all I want to know is what transformation occurred from f of x to g of x. And according to this, g of x is just the same as f of x, but then they subtracted 2. First of all, is that on the inside of the function or on the outside? Outside. So we're looking at a vertical translation. Excellent, right? So it's addition or subtraction, so now we know it's going to be a translation happening on the outside, so now we know it's vertical. Well, with the vertical, what you see is what you get. So if I see -2, that's just telling me that the whole graph is moving down 2 units. That's it, right? And so really, it didn't really even matter what f of x was or what the graph looked like. If I see that f of x -2, I just know that's going to move it down 2 units. That's really all I needed. Okay, so I can say here that this is a vertical translation 2 units down. Okay, so as long as I understand what that -2 does, then I'm good. Okay, and then I'm like, oh yeah, that looks right. So now I can look. The graph does help to kind of confirm, right? So if I look at this, I say, oh yeah, look, every single point on this, just kind of everything slid down 2 units exactly. There it is, right? From f of x to g of x. There it is. How about the next one? This one, we want to know what transformation occurred from f of x to g of x, right? And g of x is the f function, but x -2 as my input. So again, it's still addition or subtraction. So what kind of transformation are we looking at? Translation. If we're adding or subtracting, it's translation. It's happening inside, so it's horizontal, right? Good. So we're looking at a horizontal translation. And if it's x -2, we're actually moving to the right 2 units. Perfect. Good. So here I could just say, oh, okay, g of x is just a horizontal translation 2 units to the right. Okay? And it's because I know how to read what that right there is going to do. Okay? And then I'm like, oh, okay. Well, I could see that. Basically, this is f of x. If I move every one of these points, 2 units over to the right, that is where I land. Yeah. But don't y'all agree with lines, right? If I didn't have those arrows, this could have easily looked like a vertical, couldn't it? Like it could have looked like I just took this line and also moved it up. So that's why it's important to look at the equation much more than to the graph. Okay? The graph can be a little misleading. Okay, how about here? We still want to know, same thing, what transformation happened from f of x to g of x. Okay, and I see that g of x is still the f of x function, but I'm inputting a negative x. So what does a negative do as far as transformations? It reflects, right? So that negative right there reflects. Okay, and if it's on the inside, are we looking at a vertical reflection across the x-axis or a horizontal reflection across the y? It's going to be horizontal, right? So basically, it's looking like this f of x is getting reflected across that y-axis, and any value like this right here was a positive 1x. That gets reflected over to negative 1x. I mean, not negative 1x, but just negative 1 for x, right? So we're just reflecting side to side horizontally, but it's a reflection across the y-axis. The y-axis is acting as our line of reflection. Okay? All right. What about from this f of x to that g of x right there? What are they doing here? Are they adding, subtracting? Did they change the sign? Did they multiply by a number? They're multiplying by a number, right? So this is our a. They're multiplying by a number a. This is going to be stretches and shrinks, right? It's happening on the inside, so it's horizontal. Okay, so we're looking at this from a horizontal perspective. Okay, so from a horizontal perspective, a number less than 1 is going to be a horizontal stretch. Very good. Awesome. So that's going to be a horizontal stretch. It's like if I had taken this f of x and then just kind of stretched this graph. Imagine that this graph is like on a stretchy surface and I stretch out away, I pull it away, it would kind of make it look flatter a little bit, right? And so if I stretch out horizontally, and what's our scale factor? What is our stretch factor? So by 2, good, it's got to be the reciprocal. So this is a horizontal stretch by a factor of 2. It's got to be the reciprocal of that a value since it's a horizontal. All right, good. How are we feeling about these? Thumbs up, down? Okay. I like it. Okay. Try 5 and 6. Think about what those might do. All right. Ask yourself, is it addition or subtraction? Because that's translations. Did they change the sign? Because that's a reflection. Or did they multiply by an a multiplier? That would be stretches and shrinks. Okay. And decide, is it vertical or horizontal? And see if you can describe what they're doing here. To get from f of x to g of x. Does anybody want to give number 5 a shot? Yeah. Perfect. Okay, so she said she got a vertical stretch by a factor of 2. Do we agree? Yeah. So we have a multiplier a. That's what we're doing. G of x is f of x multiplied by 2. So we're multiplying by a value of a. It's happening on the outside, so it is vertical. And for the verticals, it's a little easier. It's what you see is what you get, right? So if we see that a value of 2, which is greater than 1, we just know this is a vertical stretch by a factor of 2. Okay? Awesome. What about number 6? This is our original f function. According to them, g of x is just 1/2 f of x. What type of, anybody want to give this one a try? What transformation is this? Yeah. Yeah, it's a vertical compression. So again, it's happening outside of f of x, so it's vertical. It's a multiplier. We're multiplying by a value a, so that's a stretch or shrink, and in this case, it is a compression or shrink. And it's exactly the same scale factor. With the verticals, what we see is what we get, right? So this is a vertical compression or shrink by a factor of 1/2. That's exactly what we see. We only have to do the reciprocal for the horizontal ones. Okay? All right. This one, we're doing our own graphing, and then we'll describe. Okay, and that's fine. We'll graph it. It's good review to graph a line. We haven't graphed a line in months. But really, we know that the easier place for us to decide what transformations happen, the easier place to see that is here in the equations originally, more so than on the graph. Okay, well, let's go ahead and graph this because we haven't graphed in a minute. So it does tell us to graph f of x equals x and g of x equals 3x minus 2. So here's the deal. F of x equals x, just a reminder, is the same thing as y equals x. And guys, that is the parent linear function. So we've talked a lot about the parent quadratic. This is the parent linear. This is the original, most basic, first ever linear equation. All other linears can be thought of as transformations of that guy right there. Okay? So if we look at y equals x, and it just says y equals x, what's our y-intercept? 0, right? So this passes through the origin. Okay? And what's our slope? 1. Good. So that means that from this y-intercept of 0, I'm going to move up 1 and forward 1, right? Up 1, forward 1, up 1, forward 1. This right here is the parent equation graphed. Okay? This is as simple and as basic of a line as you can get right here. That's f of x, the parent. Okay? Basically just this perfect 45-degree positive line. All right, g of x has a y-intercept at what? -2, and our slope is 3. That tells me from this y-intercept I'm going to move up 3 and forward 1, up 3, forward 1, down 3, back 1 if we need to. And so this guy is over here. There's g of x. And that's fine. We graphed it because they asked us to graph it, and it's good review. But the reality is that when I describe this, I really probably want to focus over here on the actual equation, right? So if the original was x, and then g of x took that x value and multiplied it by 3 and then subtracted 2. There's no parentheses here, okay? It's just that whatever x was, which was our, x and f of x are the same, okay? What happens when we multiply that by 3? What does that do? When we multiply, it's a stretch or shrink, and this is a vertical stretch, right? So one of the transformations here is a vertical stretch by a factor of 3. Okay, is that all that we did? No, what does that -2 on the end also do to our line? It translates it down 2 units, right? So the other thing that we did was a translation down 2 units. Okay? All right, excellent. And that's a lot easier to do from the equation, really. Okay? All right. This right here, this next set of problems really gets at the heart of the fact that it doesn't really, or it's not necessary, I should say, to have the graph in front of us to know what transformation happened. So here, we're still doing essentially the same thing. We're describing what transformation occurred from the function f to function g. So we're just describing the transformation, and we don't have a graph in front of us. And the whole point of that is it's okay, because we can figure out what transformations happen from these, these f of x hints over here, right? So I'm going to give you guys a minute or two. Try these 4. I'll give you all like a 20-second head start here. Try them out. So on number 8, you have this f of x function. Happens to be -3x plus 5. Cool. But then g of x is just that f of x with an x minus 3 in our input. So think about what transformation that would cause. Okay? You have your notes and your little cheat sheet if that helps. Any ideas on what an x minus 3 inside the parentheses is going to create? Kayla? So it's horizontal, so 3 units. Right, there you go. Yeah, so it is absolutely right. So if it's addition or subtraction, we know it's a translation. And if it's on the inside, we know it's horizontal translation. So I agree wholeheartedly. So we're looking at a and if it's a horizontal translation and I see x minus 3, that actually means we did a horizontal translation 3 units to the right. Very good. Okay. What about on number 9? Okay. Are they adding, subtracting? Are they multiplying? Is there a sign change? G of x is just the same as f of x, but you have a 4/3 x as our input. So what do y'all think that's going to do? Vertical or horizontal, first of all? Horizontal. Okay, are we adding and subtracting, or are we multiplying? What are we doing? Multiplying, so this is a stretch or shrink. Okay, so we're looking at horizontal, stretch or shrink. So now let's think about that a value. If that a value is 4/3, which is greater than 1, this is going to be a horizontal compression or shrink. by a factor of what? 3/4, right? We have to do the reciprocal. Okay? So we're looking at a horizontal compressing in by a factor of 3/4. Yes? What's that? Well, A is 4/3, but remember our scale factor for horizontal stretches and shrinks are always the reciprocal. We have to do the reciprocal, right? So A is 4/3, but our factor of compression is 1 over that, so it's the reciprocal of that 3/4. Okay, good question. Okay, what do we think is going to happen on number 10 if g of x is 1/2 times f of x? Yeah. Yes, that's a vertical compression by a factor of 1/2, right? Same thing. So what we see is what we get. So this is on the outside, so it is definitely vertical. It is a multiplier, so it is a shrink or stretch, and in this case, you're right. It is a compression or shrink. So vertical compression by 1/2. Okay? What's this last one going to be? What do you think? This is a vertical translation. So it's on the outside, so it's definitely vertical. And it's addition or subtraction, so it's a translation. So it's a vertical translation by what? How many units? 3 units. In what direction? Up, right? Vertical, up and down. So plus 3 just goes up 3 units. Okay? Okay, check it out. Look at this word problem because it looks really wordy, but guess what? It's the same thing. So don't let that intimidate you. They tell you all this stuff about how the total cost in dollars to rent this canopy D days is given by that function because you have a $30 setup fee and a daily charge of $15. Then they tell you that the setup fee increases by $20 so that the new setup fee is just the same as the old one plus 20. When it's all said and done, they just want you to describe the transformation from C to T. So what does that plus 20 do? It just translates the whole thing 20 units up, right? Okay, so for this one with that plus 20 on the outside, we would just describe this as a translation 20 units up. And I really should say a vertical translation. Translation 20 units up. All right, on these, we're going in the opposite direction. Instead of being given the function and describing the transformation, we have a description, and we want to write what that would look like for g of x. So if we do a horizontal shrink, right away we know we're multiplying here by a on the inside of the function. It's horizontal, so it's got to be on the inside of that g of x, and it's a multiplier since it's a shrink. So we're looking at something that essentially looks like that. If our factor is 2/3, we know that that's really going to be the reciprocal. So here I could say g of x is just the f of x function multiplied by 3/2 x. And that would achieve that horizontal shrink or compression by that factor of 2/3. On number 14, the graph of g is a horizontal translation. So I know I'm looking at something where inside we are moving it side to side, adding or subtracting depending on the direction. So if it's going to be a horizontal translation 5 units to the left, then I know I can write that by describing g of x as just f of x plus 5. And that would cause a horizontal translation to the left when we have that.